Welcome back again, where we were discussing angular momentum, and I want to wrap up that discussion and finish with a few more examples. So we discussed that, like linear momentum, angular momentum is also conserved. The condition for conservation of angular momentum is analogous to that of linear momentum. It is that we have no net torques on the system as opposed to no net forces for linear momentum. And based upon the equations that we discussed, we set out a definition of angular momentum, and then we also equated that to the moment of inertia times the angular velocity. And so with this equation here, basically the I omega in the initial state has to equal the I omega in the final state whenever there's conservation of angular momentum, when there are no net torques on the system. So an application of this that's very commonly stated is when you see figure skaters and they're spinning and they bring their arms in, they spin more rapidly. That's really due to the conservation of angular momentum, because what's happening is that their moment of inertia initially, with their arms spread out, is larger than when they bring their arms and tuck their arms in. This makes their moment of inertia smaller, and therefore, to make up for that, their rotational speed has to increase. You can do a little version of this at home if you have a spinning stool or a spinning chair and you hold some weights in either hand. Get yourself spinning and then bring those in, and you'll notice that even without trying, you will be spinning more rapidly. Another application of this we discussed in the example last time about Neptune, that when planet formation takes place, you go from this moment of inertia where it's more of a disk to where the rotation is rather slow, to compact objects or planets that have a lower moment of inertia and are thus moving faster in their orbits than any of the disk rotation was. And if you've ever watched diving or gymnastics, you may have seen that the arms of the athlete are sometimes extended, or their bodies are curled up or stretched out at different points during the rotation, and this is all to change their moment of inertia and allow the angular speed to change as a result, based upon this idea of conservation of angular momentum. One more application of this that's kind of interesting is in skateboard tricks. There's a link here to a YouTube video by Physics Girl in which she explores this, and it's actually pretty interesting. By the way, she's also going to talk about the mid-axis theorem that we discussed before in this video, so I encourage you to take the time to click on that link and have a look. Okay, so I promised you a couple more parting examples. Let's take this one to start with, where at a playground a child is running and jumps onto a circular merry-go-round platform, as you may have seen in playgrounds. So this problem actually is very similar to the sticky ball that stuck to the wheel kind of problem. There's only a slight difference here, and that's that the child was moving tangentially to start with at that radius. Remember, we had to figure out what theta was. In this case, we're going to have theta equal to 90 degrees. That is to say that if you take a bird's eye view of this circular platform, and it's rotating, say, maybe this way around, the child is coming in like so and hitting right here, so that their initial momentum P is in this direction and the R vector is that, and so you see that theta is going to be equal to 90 degrees. All right, but our objective is very similar. We want to know what the angular velocity of the platform is once the child jumps on, which is a similar question we asked with the sticky ball and the wheel. How fast was it spinning? So in order to do this, we're going to take a similar tactic where we look at the moment of inertia of the entire system. In the initial state, it's just the child who has linear momentum. which we can look at in terms of the angular momentum. And then in the final state, the child that we can treat as a particle rotating about the center gets added to the moment of the inertia of the disc-like shape of this merry-go-round. So in the initial state, then, this platform is not moving, so we can take that out of our sum, and the only thing that has momentum, angular momentum, will be the child. Okay, and we said that because this is going to be r cross with p, this will equal r mv sine of theta, but theta we said was 90 degrees, so this is just 1, and so that's where we get this value right here. Okay, then the platform in the final state, we don't actually have to plug in some 1/2 mr squared or anything for the moment of inertia, because we are actually given a numerical value for this. So I wanted to give you an example in which that's the case as well, because sometimes we're just so used to looking up on a chart or trying to figure out what the moment of inertia is for a certain object, but occasionally it's just given to us as a number. So I can just leave that as I for the merry-go-round, and then the child's moment of inertia is here. Since they are being treated like a particle, it's just mr squared. Okay, so when we equate the initial state to the final state, we get the following expression. And when we simplify and plug in the numbers that were given to us in the problem, we come to the conclusion that the final state is that the merry-go-round is rotating at an angular speed of 1.78 radians per second. Okay, so one last final problem for you. We are going to take a situation in which we have a table with a hole drilled into it, and hanging underneath the table, so this is what the table surface would look like. Hanging underneath the table is a mass, which is attached by a string to a puck that is then going around a circle on the surface of the table. Okay, it sounds like a little bit of an elaborate setup, but this kind of problem is sort of a classic physics problem, and so we're going to examine what happens in this case. So let's say that initially the puck is traveling with a tangential speed of 2 meters per second, but then the cord is being slowly pulled from below underneath the table until you have a radius, which probably should have a subscript f there, of 0.1 meters instead. And so we want to know what the speed is once this radius has decreased to 1/10 of a meter, and we also would like to know what the tension is on the cord at this smaller radius. So for the first part of this, we're going to use the conservation of angular momentum, and for the second part, we will just use Newton's laws and what we know about tension. But first, it's important to mention, speaking of tension, that the tension force we're not going to consider to be exerting any kind of torque about this hole around which this thing is rotating. Why? Well, it is pulling in this direction and the rotation is in that direction, so it's right at the axis of rotation, so that R value in your lever arm is actually equal to 0. Okay? But we do want to examine what's happening with the angular momentum of the puck. So in the initial state, if we do R cross with P, then this should be, the magnitude of this should be RMV sine of theta, and theta is going to be again equal to 90 degrees in this case. Another way to look at it is to approximate that the rope is massless, and we can take this to be L equal to I times omega, where I is like a particle, mr squared, and then omega is v over r, and you see that we get back this same equation here. Okay, either way you slice it, the initial state and the final state have very similar expressions. It's just that the r and v values are changing. So when I combine this and set the initial angular momentum equal to the final angular momentum, I get that mri initial, vi initial must equal mr final, v final. The mass, as you see, cancels out. And then when I solve for the final velocity, I find that the final velocity of the puck at this smaller radius is 4 meters per second. It was only going 2 meters per second to start with, but we see now that this has shrunk. It is now 4 meters per second. Okay, what about the tension for part B? Well, for this, you can think about centripetal force, and the tension is connecting this weight to this puck. So the tension is the same here on this puck as what it would be on this mass, right? So you could do a free body diagram of this mass and, think about the fact that, tension would be up and the weight force down, and that would be equal to m times a and so on. But you could equally well look at the puck and apply Newton's law there, where if we can ignore friction, then all we have is the tension force pointing in towards the center of the circle and providing a centripetal force. And in that case, that is the sum total of our forces in that direction, equal to m times the centripetal force. And when I then solve using the final velocity that I just figured out was 4 meters per second and the final radius of 0.1 meters, I find that the tension on the rope is 80 newtons. So this concludes the lectures related to Unit 6. Starting with the next lecture, we will begin Unit 7.